So I've actually been thinking about organic chemistry a lot this morning, based on my condition. I don't know if you guys have noticed, but like I have horrible allergies, which is why I'm wearing my glasses in the morning. I don't know if you guys pay attention at all, but I'm wearing my glasses in the morning and my contacts in the afternoon because I can't handle springtime. Like the pollen in the air just is kicking my butt right now. And the reason why this has been on my mind recently is that I've been looking into different medications to try to help alleviate my runny nose, my eyes are horrible, I'm sneezing all the time. And so like I have a bag that's got like eye drops, a nasal spray, I'm taking a decongestant. And as I'm thinking about this, I feel like that's appropriate based on organic chemistry because all of those fit under the umbrella of what's considered to be organic. So organic in other terms of the word, like organic in the farming industry means that it's grown without pesticides, right? Is that pretty much the definition you'd use? Okay. But like organic in the chemistry definition means carbon-based. And so many of the different drugs and compounds that you'd get, like say from pharmaceutical companies, they're carbon-based. And I'm so thankful that, for my allergies, that at least I have some sort of relief that I can go into the pharmacy and buy Claritin and that makes it just a little bit better. And that's really based on the study of organic chemistry. This first slide I have on here has 3 different compounds that I wouldn't expect you guys to recognize just off the top of your heads, but some of these have radically changed our world. So let me talk to you about what they are, and I hope I still remember them all, because every year I always have to remind myself. Let's start with this one right here. This is a compound that some of you may have actually researched in the first unit. It is a compound that has 3 of these little groups on them. See how there's 3 of them there? And so its name starts with tri because there's 3 of them. And then these groups would be known as nitro groups. And then the rest of this molecule right here, the rest of this thing here, is known as a toluene. Does anybody know what trinitrotoluene is?
TNT.
It's TNT, yeah, dynamite. Yeah, an organic-based molecule. Right, now, the discoverer of TNT has really changed the field of explosives, demolition, anything that has the ability to, I don't know that combust is the right word here, because combustion usually involves oxygen gas and produces carbon dioxide, but like the ability to blow stuff up, that's trinitrotoluene. Okay, this molecule right here, I'm fairly confident I remember what it is. I believe this is aspirin. I believe. I read somewhere, Melissa's a nurse, she said that if aspirin nowadays were to be developed and synthesized in the lab like years later than it originally was, she figures that there's studies that say that it would probably cost you like 20 bucks a pill for an aspirin because it would be that expensive. But the good news is that it was discovered so many years ago that now there's all sorts of other knockoff companies that can make like generic brand drugs. You know what I'm saying there? And so now it's actually fairly cheap for you to go to, say, Shoppers Drug Mart like I did, and I can look at buying one type of drug, and then right next to it is like the generic brand drug that's like the exact same medical ingredients, only $2 cheaper. You ever looked into that? Right? Like if you were to buy like the Tylenol brand acetaminophen, and then you buy the Life brand acetaminophen, as I compare the medical ingredients, it's like 500 milligrams per tablet, regardless of which one I buy. But the name brand one looks kind of fancy, so maybe I end up buying that one instead. But like it's got the same chemicals inside of it. So I'm pretty sure that one's aspirin. But again, I always forget every year. This one right here, it's one of 2. I always forget which one it is. It's either Kevlar or it's Teflon. And oh my goodness, Teflon. I'll go look it up later just so I can remind myself. But do you guys know what either of those 2 chemicals is used for? Okay, so body armor for Kevlar, yeah. When Kevlar was discovered, maybe developed even, synthesized, created in a lab, they discovered that it was fairly lightweight and yet it could also stop bullets, which is totally useful to the crime fighting field of police officers who need to have, bulletproof vests, basically. Anybody know what Teflon does?
Isn't that like on non-stick?
Yeah, basically Teflon's a coating that you put on a frying pan. And it's supposed to be non-stick is the idea, right? Which has actually changed and revolutionized the way that we cook food because they used to have to cook food in like a lot of butter. If we're talking 50, 60 years ago, in order to get food to not stick to stuff, you'd grease it up like crazy so that it would come out of the pan when you were done. Well, now if you have these non-stick pans, maybe you have to use a little bit of a spray, like a cooking spray, a little bit of olive oil, but you don't need nearly as much to try to prevent the burning to the bottom of the pan concept. Does that make sense? All of these are organic. In my opinion, this unit here, the organic chemistry section, I think this is the most important one of like all of the science topics I teach. Like if I wanted to include all of physics, all of chemistry, all of math, I think this one has changed our lives the most. When I think of like the inventions, the innovations, especially the drugs that have been developed in the organic chemistry kind of thing, like I can't imagine what our world was like before these sorts of things. Does that make sense? So this unit here, what we're going to do is we're going to talk about three main things. The first one is we're going to talk a little bit about just where some of these developed, synthetically created, sometimes they're plastics and polymers. We're going to do the lab where we create artificial smells. But we're going to talk about like where those get used, and hopefully you'll realize that like as you look around the classroom, a lot of the stuff that we have that's technologically based is really based on scientists, chemists who developed work in this industry. I mean, as I look at your water bottles, those are carbon-based. Those are probably plastic polymers. You don't just naturally mine plastic out of the ground. You create plastic. Does that make sense? No. The clothes that you're wearing, many of you are wearing clothes that probably contain polyester. Polyester is not like cotton or wool. Those are usually kind of itchier. They don't really retain their color quite as well. They're synthetic fibers that have been created that we now use when we make our clothes out of them instead. Does that make sense? They're carbon-based. They're not. You don't mine polyester out of the ground in the same way, or you don't raise sheep that grow polyester like the same way that they grow wool. So that's one thing we'll talk about. Second thing we're going to focus on, and most people really like this part of the unit, we need to learn a whole new naming system. Okay, I showed you the name up there for trinitrotoluene. You know how you've learned how to name things like calcium chloride or lithium phosphate? There's that naming system. There's actually an entire other branch of how to name carbon-based compounds that I've never had to show you before until now, obviously. And you probably know a few of these already. For example, methanol, ethanol, methane, octane. Those are some of the compounds that actually have a different systematic naming scheme that you might recognize already. So we're going to learn about that naming scheme. Does that make sense? Then the third thing we're going to talk about, and this is mostly towards the end of the unit, we're going to talk about the types of chemical reactions that we use in order to create the cool compounds that we want to make. Does that make sense? And so previously you guys should have learned formation, decomposition, single replacement, double replacement, combustion, neutralization, redox. Like those are some of the reactions you should know so far. Well, we're going to add some new ones. The main ones we're going to add are called a addition reaction, a substitution reaction. We're going to talk about condensation, polymerization, esterification. So we're just going to learn a whole bunch of new reaction types. And in a way, we're just giving you just a glimpse into a whole new branch of chemistry, where it has an entire different naming system, an entire different types of reactions that occur. And I don't know, I find this stuff cool. I really think it's fundamentally changed our world. When I look around and I look at especially the drugs that we take and go, they didn't have those 100 years ago. When I even look at my wife's work, Melissa works on the obstetrical floor, so like the baby labor and delivery floor. When I think of the fact that they can give a pregnant person an epidural so that they're not so much in pain, and give them a drug that's safe and healthy for a baby but helps make childbirth easier. Or the fact that they're able to administer a drug so fast that if they need to do a stat C-section, like when Cameron was born, my second, we needed to have a C-section. For them to be able to knock Melissa out, but she's still awake, but just to be able to give her like the spinal, and then be able to have the right drugs to be able to cut into her stomach, physically take my daughter out and sew her back up again, give her the medication to be able to recover from that. Like hundreds of years ago, to be honest, the way Cameron was born, Melissa and Cameron would have died 100 years ago. That's just how Cameron was born. She came out half sideways. It didn't work. We needed a C-section. And I feel so blessed, and it's so cool to see the changes that chemistry and science have had on our society. So, okay, I digress. Let's get started. I could talk about this forever. So here's my intro slide. A lot of words. You guys can read it. But I want to highlight some of the cool things I've been talking about. All of the different compounds that are carbon-based. And I think this is a really good word here. Many of them are synthesized in laboratories. When I was in university and I took chemistry because I was a chem major, I remember hearing my chem professors talk about how, like, part of their jobs, other than teaching us students, was to go and try to create a new compound and see what it would do. And all of a sudden, you discovered by accident that you were trying to make this, and instead you make this really cool thing that does something else. I heard a story, I hope it's true, it may not be, but that NASA, or I think it's probably NASA, was trying to develop some sort of really good bonding agent. Like, basically a really solid glue is what they were trying to create. Probably carbon-based, they were trying to synthesize it. And one of the trials they had ended up producing the sticky stuff that goes onto sticky notes. Which is weird, because the stuff on sticky notes is not a good bonding agent at all. Like, it's not very firm for sticking. And yet you can take a sticky note and peel it on and off probably 100 times, and it's still going to work. You know what I mean? And like, that's a synthesized chemical that someone created. That one I think was by accident though. So, ended up making like standard. Interesting, cool. Yeah, that's actually I think one of the ones on this list here. Yeah, they're artificial flavorings. So we're going to do artificial flavorings in our lab. We're going to make esters that basically have the same chemicals that maybe you would have in a stick of gum, for example. When you guys would take a bite out of spearmint gum that tastes like winter fresh, they didn't just take a whole bunch of peppermint leaves and like squeeze them into the gum, right? Or if you have strawberry flavored or cherry flavored gums, they didn't go buy a whole bunch of cherries and like drip that drippings into the gum. They used a chemical that synthetically tastes and smells. Heck, even the gas we use in our car is technically organic in the fact that it's carbon-based. Medicine, to me, is the one I've been talking about. That's fundamentally changed our lives, without a doubt. Plastics. You don't get plastic out of the ground. Like, we don't go mine plastic. We actually have to produce it using a process. And I think that's actually both good and bad for the environment. Probably bad for the environment in that sometimes if we don't recycle our plastics, then it builds up in our landfills, right? But maybe better in a way that plastics are lightweight. Sometimes they're cheaper. So sometimes it's actually better to package things in plastics because it will keep things fresh for longer. Or, for example, if we use plastic to try to keep things sterile, like when my wife ends up working on the obstetrical floor again, they need to have sterile instruments. Often they've been cleaned and then they've been plastic wrapped so that when they open them, they know that they are ready to use instantly. Does that make sense? Okay. This line right here is the one that blows my away. The number of known carbon compounds exceeds the total number of all compounds combined. You know how I've been teaching you chemistry now for about a year and a half? This one unit we're going to talk about, if you want to keep going in organic, is larger than all of the rest of chemistry we've been talking about combined. So it's kind of groundbreaking. Like, we're going to have to almost start from scratch. We have to relearn how to name things. We have to relearn how to like know what the chemical formulas are for like a whole different side of chemistry. Okay, so what you guys need to know is what I've already said here. It's carbon-based. If something involves carbon, it's considered organic. Carbon is very unique for one specific reason, and it's right here. Carbon atoms can form 4 bonds. It's actually a really cool thing. Way back in grade 11, we would have talked about how to like draw some bonds, and maybe you'd have drawn Lewis dot diagrams of different elements. You guys remember doing stuff like this? Carbon's the coolest one because carbon has 4 bonding electrons. And in having this property, carbon can replicate and bond to itself a lot. For example, I could bond this carbon to another carbon, and I could then bond this carbon to another carbon, and this carbon to another carbon. Essentially, carbon can just keep bonding to itself over and over again as much as you want it to, because there's a lot of different bonding electrons from each carbon that you have. Does that make sense? Oxygen's a little less likely to do that. Like, I could bond this oxygen to another oxygen here. I guess that might work. But there's only like, say, one free bonding electron off of each side of the oxygens. Whereas look at my carbons here. I've got all of these open slots right here where if I wanted to make more bonds.
Marley Duncan, can you please come to the office?
And so it makes it very
Marley
large.
Duncan, please come to the office.
It gives it the capacity to make very large, convoluted, complex molecules. And like I said, sometimes we discover one of these molecules is aspirin, and that can help someone from like, they won't die if they have a heart attack anymore. Right? Groundbreaking. We're going to talk about how carbon can form chains and rings in this course. But carbon can actually form tubes as well. Now, we won't talk about that very much, but has anybody ever heard of like carbon nanotubes? Okay, if you've heard of that before, like, again, like in the last probably 20 years, the ability to make some of these sorts of things that are like resistors in computers. Anyways. Where does all of our energy come from? Yeah, we learned that in our first unit, right? All of our energy comes from the sun. And at the end of the day, it kind of falls into like a bit of a loop here where once we get it from the sun, plants probably is the best place the sun helps them grow, right? So photosynthesis uses the sun's energy, causes plants to grow. And then the plants, maybe they get eaten by they get eaten by animals. The animals use carbon dioxide. At some point, though, we've talked about how, plant and animal matter would decay. It would get buried underground for, thousands of years, and hopefully it would turn into our fossil fuels. Well, our fossil fuels are like our oils, our gases. That's actually the basis of where most of our organic stuff comes from, is actually fossil fuels. Environmental stuff is really big these days, right? Where they say we need to leave the oil in the ground. And although there's some benefits and pros and cons to that, one thing that I think always gets missed in that debate is the fact that we need our fossil fuels to produce anything that's plastic, anything that's synthetic. We actually need those oils as the starting point because they're carbon-based. That makes sense? So maybe we don't need to use all of those oils for burning them as fuels to like make our cars and trains go or to heat our houses. But if we were to leave all of the oil in the ground, we wouldn't have drugs. We wouldn't have plastics in our cell phones. We wouldn't have calculators. You wouldn't have a Tim Hortons cup because we would need that oil to make those. Does that make sense? So. Okay. Some definitions you guys are going to need to know. Organic chemistry then. Anything involving carbon. With 4 exceptions. And they actually like to give this question on the diploma quite a bit. They're going to give you a list of chemicals. They'll say which of the following are organic compounds. And so if you see a carbon in it, it's organic. But there's just these 4 exceptions. If there's a carbonate, it's not organic. What's carbonate? CO3, yeah. So here's an example. CaCO3, calcium carbonate. You even know how to name that. If you know how to name it using an old-fashioned naming scheme, it's probably not in the organic naming scheme. So this would not be organic. I know it has a carbon in it, but it's not organic. Okay. Cyanide. Anybody know what cyanide is? Okay, but anybody know what the chemical formula? It's a polyatomic on your sheet, by the way. You have your data book with you, bud. Many cyanides, though, they are poisonous, yeah. CN, yeah. So if I were to give you NaCN, for example, that would be called sodium cyanide. Again, I just named it using an ionic kind of naming scheme. It's out. So that's not organic. Carbides. A carbide, if it ends in IDE, that's where ide would be like chloride, sulfide, phosphide, carbide. It means that it's the second half of an ionic compound, like say CaC2. That's calcium carbide. It's ionic again, doesn't count as organic. And then the last exception that doesn't count as organic is an oxide. Anyone have a guess as to what an oxide might be? That'll be it. Yeah, that's one. CO2, carbon dioxide, doesn't count as organic. And the other one is carbon monoxide. Those also don't count as organic. Again, we can't name those under the organic branch because you already know how to name those. Those are ionic and molecular compounds. That makes sense? So let me draw you some compounds, though, that are organic. CH4. Name that. Methane. It's a name that back in grade 10 or 11 I probably told you to memorize. The reason why is that we haven't learned how to name its organic name yet, but it doesn't fit into like a 2-word naming scheme like everything else does. I mean, yes, it's molecular, but we don't call it like carbon tetrahydride. Here's another one, CH3OH. What's CH3OH? It's methanol. Yeah. Again, methanol is something that you have learned how to name before, I guess, but only because I told you to memorize it, because it has a different naming scheme. This is an organic compound. It contains a carbon in it. That makes sense? Okay, we'll keep going. One of the things that we're going to spend some time talking about is the refining process. This is really applicable in Alberta. If we're going to get these carbon-based substances to then use to create plastics and drugs and trinitrotoluene, whatever it happens to be, first we need to obtain the raw chemicals. And so refining would be just a generic word that involves the chemical and physical processes for separating them into, like, separating the mixtures. So we can crush up coal. We can separate, maybe you know these words from previous years, like distillation, condensation. We'd have to separate natural gas out. We're going to talk about the oil sands a little bit later. I actually have a day where we're going to talk a bit about some of these processes. But yeah, the oil sands are actually critical to the organic chemistry field in terms of getting the raw products we need. Let's move on, though. I think this is just a slide I threw in here just to show you all of the different types of hydrocarbons that you could have. You could have coal, you could have oils of some kind, you could have natural gas, which we usually use to heat our houses. Okay, let's start naming stuff. I found that I made this slide a while back to help with the naming process. We're going to branch off into all sorts of different naming schemes over the next 3 weeks. So when we start, we're going to start off on the left-hand side with anything that's considered a hydrocarbon. If it's a hydrocarbon, it's going to have hydrogen and carbon in it, and that's it. Okay. Later, we're going to get into the hydrocarbon derivatives, and then it can have hydrogen and carbon plus other stuff. Okay. So, for example, when we did methane, CH4 methane would be considered just purely a hydrocarbon. But if I gave you methanol, which was CH3OH, that's a hydrocarbon derivative because it has hydrogen carbon plus something else. Does that make sense? Okay. In the hydrocarbons field, we actually have 2 different paths we can take. Today, we're going to hopefully talk about things called aliphatic compounds. And then tomorrow, we'll talk about things that are aromatic. And it's a little easier for me to talk about the difference between the two once I show you what a benzene ring is. But just as a bit of a heads up, I can show you one back here. This thing right here in the middle, that's known as a benzene ring. So if it happens to have one of these fancy little circular things in it, then it's considered aromatic. If it doesn't have one, it's considered aliphatic. So to start with, we're not going to have anything that has this special ring in it for today, but we'll get there tomorrow. Does that make sense? The last thing I want to talk about on this slide here is if we're in the aliphatic section, we can talk about alkanes, alkenes, and alkynes. And the way we label those is based on the types of bonds there are. If it only has single bonds, it's an alkane. If there is even just one double bond between carbons, it's an alkene. And if there's a triple bond, it's an alkyne. Why can't we have a quadruple bond? Yeah, there's only one compound I've ever heard of that can have a quadruple bond. It would be carbon attached to carbon, where you'd have 1, 2, 3, 4, 5, 6, 7, 8, and you'd have to bond that one, that one, that one, and that one. And now there's no other electrons left for bonding. So maybe you could have a carbon in a group of 2, but that's about it. You can't keep bonding if you bond all 4 of your electrons. So far, so good? Okay. Here's a slide that shows some of the different ways that we can do formulas. You hopefully have seen this before because this is actually directly out of your grade 11 notes. Okay. Sometimes we write things in their molecular formulas like C6H14. Is this going to be a organic compound? Yes, because it contains carbon. We're going to need to learn how to name that in a few minutes here. Now, we could write it as C6H14, but sometimes that's not enough information. Maybe it's better to write it like this: CH3CH, CH3CH, CH3CH3. And if we write it in this sort of format, it gives you a clue as to what it's going to look like. For example, this CH3 right here is probably this CH3 right there. And then it says CH. Well, that's this CH right there. And then it says CH3 again. Well, that's this CH3 going up like that. And there's another CH. Well, that's probably this guy right here. Then there's another CH3. That's this guy probably down here. And then the last CH3 kind of goes over there. Are there still 6 carbons and 14 hydrogens? Yeah, sure. But this formula right here maybe isn't as useful in trying to help us know what it looks like on like an individual branch sort of level. This is known as a structural formula. We're going to spend a little bit of time drawing structural formulas, but most of the time we're probably going to go to the condensed structural formula, where we write like CH3, CH, CH3, like we'll write it like this, mostly because it saves time. Later, I'm going to show you how to do the line formula, because sometimes these lines are an even more efficient way of doing things. The lines, by the way, are actually what you see in this benzene ring. These benzene rings, and even like some of these ones right here, I'm just doing lines as a shorthand way of letting you know what's happening, because it's going to save time by just drawing lines everywhere. Okay, I think I've done enough preamble. We need to get to some examples here. Find the slide here. You guys have this one in your notes coming up somewhere soon? Okay. So this slide is the first one you need for learning new nomenclature. Okay. It's based on, there's actually like 3 things you need to know here. Okay. The first one you need to know is how many carbons can you find in a row? If there's 1 carbon, it's a meth something. If there's 2 carbons, it's an F something. We have an ending we put to it. Okay. So that kind of gets things started. If there's going to be branches of things, I'll show you a branch in a second. A branch is known as like a methyl or an ethyl or a propyl branch. So for the first little while as we learn how to name these things, try to keep this slide somewhere nearby. Like we'll be flipping back and forth. Okay? So let me show you how to name some compounds. This is called methane. It's CH4. The reason why it's called methane is that there's 1 carbon. And 1 carbon has been designated as being called a meth something. The ending to the word then, ane, is because it's an alkane. It only has single bonds. If it only has single bonds, end it with ane. If it has double bonds, we're going to end it as an ene, ene. And if it has triple bonds, we're going to end it as an ine, which is yne. That's the alkanes, the alkenes, and the alkynes. So since there's only single bonds, meth because there's 1 carbon, ane because there's only singles. That makes sense? Well, similar logic here. Here's the molecule ethane. See how there's 2 carbons in a row? 2 is the prefix now F. I don't see any double bonds, so we call it ethane. 3 carbons in a row. 3 carbons in a row is called a prop. And then we end it with ane because we've only got single bonds. So far, so good? Okay. So here's some examples of the basic ethane, methane, propane, butanes along those lines. I'm going to draw a few of them for you, but I won't draw them all. We've already done methane, ethane, and propane. The next one would be butane. Butane would look something like this. 1, 2, 3, 4 carbons all in a row. None of them get double bonds or triple bonds. The reason why none of them get double or triple bonds is that it's an ane. Do you guys remember the octet rule? It means you need to have 8 electrons. if we draw one of these dashes, do you guys remember how many electrons are in a dash? Okay, good. So essentially, like each of these carbons, like this one right here has 2 electrons in it. So that means we're going to need 1, 2, 3 hydrogens around it. Now it's bonding in 4 directions, right? 2, 4, 6, 8 electrons. This carbon right here, though, only needs 2 hydrogens. 1 hydrogen, 2 hydrogens, because it's already got carbons on each other side of it already. So it also has 8 electrons around it. This is how you draw butane. 4 carbons in a row, and then since this is a hydrocarbon, the only other thing we're allowed to use is hydrogen. So you can't use oxygen or nitrogen yet. We'll get there. Basically, we just need to throw every other open slot with hydrogens. So there's 4 carbons and 10 hydrogens. Thanks. Let me skip down. Let's do hexane. What would hexane look like? I'll put 6 carbons in a row. And then you're going to need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens around it. What was that? Yeah, it just kind of fits. There's actually a pattern to this. Anybody see what the pattern is to the alkane series? If you have a certain number of carbons, how many hydrogens do you have? Double plus 2 more. There's actually a pattern to this. For each carbon you have, you're going to need a hydrogen for the top and bottom. Does that make sense? But you're also going to need 2 extras, 1 to cap the molecule on the left side and 1 to cap the molecule on the right side. So on one of my next slides somewhere here, I should have... Sorry, I'm skipping way ahead here. Way ahead here. Do I not have this written down somewhere? I don't. Oh, yeah, I did. Sorry, it's behind. I skipped this slide, didn't I? Okay. Alkanes have this pattern to them. However many carbons you have, the amount of hydrogens you're going to need to have is double, because you need 1 top and bottom, plus 2 more. 2 more to cap the ends. Does that make sense? So if I were to ask you to write me an alkane that has 75 carbons in it, how many hydrogens would it have to have? Good job, yeah. All right, now I wouldn't ever make you draw this molecule, but it would look like this. Carbon attached to carbon, it would do that for forever, right? Well, each of these carbons needs 1 hydrogen top and bottom, and then 1 to cap the ends. I probably should talk about this slide here. I skipped some really important stuff here. There's a word I need you guys to know, and I don't even know that I'm pronouncing it right here. I think I'm supposed to say it homologous. I think I said that right. Homologous. It basically means compounds that have very similar structure, and they only differ by how many repeating units they have. So, for example, how different does... Where's that good picture? How different is methane from ethane, and how different is ethane from propane? Aren't they really similar to each other? Only each one has just 1 more carbon and 2 more hydrogens. You know what I mean? And so you can always just add another carbon. Could I make a structure that has 11 carbons in a row? Sure. 12 carbons in a row? Sure. 172 carbons in a row? Why not? Does that make sense? So the word we have for that is, if I say it right, homologous. Basically meaning that you can just keep adding another carbon if you want, just make it longer. Okay. Another term I need you guys to know is it's considered to be something called saturated. We've actually used the word saturated in a previous section of chemistry. What happens if a solution is saturated? Yeah, you can't add any more. Maybe another word I'd use is it's full, right? A solution is full if it's saturated. These compounds that I just drew here, they are full of hydrogen. There's as many hydrogens attached as is possible. I'll show you later some examples of things that are not considered saturated, where they're not as full of hydrogens as they could be. But these guys are considered full. A few other thoughts here. They are non-polar. It's been a while since we've done this, but do you guys remember how to determine if something's polar? Shape is a good part of it. The other part is electronegativity. Let me just use this guy right here as an example. Carbon and hydrogen. There is a winner to that electron fight. Carbon is probably at 2.6 in electronegativity, and hydrogen is at 2.2. You guys remember doing this? So I believe carbon wins every single fight. But because the molecule is symmetrical, it means that overall the molecule is nonpolar. What does that mean? Well, nonpolar things will not dissolve with polar things. So most oils and gases are nonpolar. They usually don't dissolve in water. So if you ever spill like some gasoline, like if you're out boating, you spill a little bit of gasoline on the surface of the water, it doesn't dissolve, like it just sits there on top. Does that make sense? It's because the gas is probably nonpolar, the water is polar. Okay, let's do some practice here. I'm going to draw some molecules, you guys name them. By the way, sometimes to save time, I'll draw a little line like this, and I won't write a hydrogen. But it implies that there's a hydrogen at the end of it. Do you guys think you can name this molecule?
Pentane.
It's called pentane. Yeah. Why is it called pentane? 1, 2, 3, 4, 5 in a row. Pent. And then no double bonds makes it an ane. Well, what I want to show you here is a molecule that has the same molecular stuff in it. This would have 5 carbons, and it's going to have 12 hydrogens. Double the carbons, add 2. I'm going to draw you a molecule now that has the same stuff, but it's a different name. How many carbons are there total?
5.
There's still 5 carbons. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens still. This has the exact same formula to it, but this is a different compound. We're going to name this thing a methyl butane. That's actually what this thing would be called. Breakfast for me. Okay, let me see if I can explain why it's called a methyl butane. Actually, anyone wants to hazard a guess as to where the butane part came from?
I was like trying to put it together. The scene, the board.
I think we're good though. Thanks, guys. The butane, you're right. It comes from the fact that there's 4 carbons in a row right here. I would call that like the stem of a molecule. This guy right here is known as a branch. See how there's kind of a branch hanging off of the main tree? Well, how many is in the branch? 1. And I know it's been a while since I've been on this slide here, but if there's ever a branch, we call it a methyl if there's 1 in the branch. If there's 2 in the branch, we call it an ethyl. Now, if there's more than 1 branch, we sometimes use multipliers of dis, tris, and tetras. Maybe I'll try an example of that in a second. What was that slide I was working on? Did that make sense, though, that I had another molecule there? Let's try naming a few more. Honestly, the first couple of days here is going to be a lot of me just giving you examples, seeing whether you pick up on it. So let's try to name this compound here. Sure, let's try naming this one here. Actually, no, let's make it even more fun. Because that's what makes this unit cool, is all of a sudden once you get it, I can just all of a sudden start making it harder by adding more. Okay, so first question. How many carbons can you find in a row? 7, okay. So 1, 2, 3, 4, 5, 6, 7 in a row makes this thing known as a hept. And then since I see no double bonds, I call it an ane. This is a heptane. Well, now there's some branches off of it. Here's a branch right here. How many is in that branch? 2. Well, a branch of 2 is known as an ethyl. And we usually write that in front of it. We write it as an ethyl. But there's actually 2 of those branches. So we would call this a diethylheptane. Does that make sense? This is a diethylheptane. Let's try one more, then I'll go on to my next slide here. Did that make sense? Okay, let me try one more. I want to go back up to the one I just drew earlier, the C5H12. I can do 5 carbons and 12 hydrogens another way even. I'm going to draw this molecule here. So again, all of these little lines that I'm drawing here, they imply there's a hydrogen at the end. I just do that to try to save on time, because I don't want to write hydrogen on the screen. Could you guys name this thing now? So I'd say work from the back. The back of the word is the ane, een, or ein. Do you see any double or triple bonds? Okay, so the end of the word is going to be ane. Then we need to know how many can you find in a row on like a tree branch. And I think the best you can do is you can find 3. So that makes it a propane. However, unlike just a regular propane, this one has a few branches off of it. There's a branch up here and a branch down here. So since there's 2 branches, it's a di. And then how big are each of the branches? 1, so methyl. This is called a dimethylpropane. Oh yeah, we're gonna do lots of practice.
It doesn't matter if the 2 carbons are just formed into 1 carbon or the 2 carbons.
Like here, the branches were both branches off the same carbon. That's allowed. But you could actually have the di off of 2 different branches as well. Okay. Yes.
Would the stem of the compound always be really horizontal in the...
No, I've actually got some examples I'll show you later, which are twists. Why don't I do it right now? Good question to ask. Here is a compound. Well, let's start with this one here. Here is not the name for this. You would not call this a methyl butane. That is not correct. Some kids would look at this and say, hey, look, there's 4 in a row. And look, hey, there's a branch off the end of it. The reason why is there's not actually 4 in a row. There's actually 1, 2, 3, 4, turn the corner. There's actually 5 in a row if you're allowed to turn a corner. Okay? And one of the things that I hopefully have shown you guys last year in grade 11 is that when we try to draw things on paper, we're drawing them in 2 dimensions. But molecules are actually in 3 dimensions. And so just because something turns the corner, that's fine. It's still all in a row. So you would not call this a methyl butane. You would call this a pentane because I actually have 5 things in a row. Does that make sense?
Does it have to be at the end for it to be able to turn it forward?
No, it doesn't have to. Like, I might draw a molecule that looks kind of like this.
Oh.
Okay, let's name this one. Okay, so assume that everything else has a hydrogen. How many carbons can you find in a row? You could go like, say, 1, 2, 3, 4, 5, 6. And I guess you got 2 choices. You could go 7, 8, which is probably what I was originally going with, right? But actually, I can go 7, 8. I can find 9 in a row. So working backwards, this is going to be an ane because there's no double bonds. The one that's longest. You need the longest carbon chain you can find. Then 9 is nonane. And then lastly, if all of this is kind of your main branch, I know it's kind of going around the corner. As you guys get more complicated, you'll discover things can go in circles. They can, they're like, if you can think, like, you're going to have this question a lot. You're going to be like, could this happen? Let me tell you this. If you can think it, it probably exists. Does that make sense? All right, but that's what's really cool about this section is you're really only limited by your imagination. And the first person who thought, hey, I wonder what happens if we try to synthesize a compound that goes around in a circle, all of a sudden discover something really cool. So, anyways, 9 in a row. What would this right here be then as a branch? Ethyl, yeah. So you'd call this an ethyl nonane. How's it going so far? Okay. But bear with me. Like, it's going to take a solid 2 days to probably get good at naming this stuff. So be patient with me if it's not. Let me talk about my next slide here for a second. It's called a structural isomer, which is where I was starting to go, and then I got sidetracked like I always do. An isomer. One kid years ago gave me a great analogy for isomers that I've been stealing ever since. Think of an isomer like a Decepticon or an Autobot off of Transformers. You guys have seen Transformers?
Yep.
Oh my goodness, the analogy doesn't work there. Okay, Transformers, where basically it's a car, and all of a sudden the car rearranges itself and turns into like a big fighting robot. Okay? Now when Optimus Prime is like a big truck, he has, you know, all of this stuff on him, right? And then when he rearranges himself though, he still has the same stuff on him, just in a different order, and somehow he's now a big fighting robot. Does that make sense? Let me go back to a couple of the examples I just had here. This guy right here has 5 carbons and 12 hydrogens. This is Optimus Prime as a truck. This guy right here also has 5 carbons and 12 hydrogens. What really has happened though is that this little branch right here has been like picked up and it's been like kind of almost moved over to the side there instead. It still has the same stuff on it, but it's been rearranged. Does that make sense? This one right here, the one we just drew, the dimethylpropane, also still has 5 carbons and 12 hydrogens. It's almost like you need to take this guy right here, throw it over on that side there instead, take this branch and throw it over there, and then yeah, you have 5 in a row.
So why do that?
Well, because they're different compounds. They have different properties. One of these drugs, like one of these things right here, might smell like perfume, and the other one right here might be used to cure cancer.
Can that
Like-
vary like the states as well? Liquid or-
Oh yeah, like one little twist can change the state. There's an example that I show you later. Have you guys ever heard of PVC piping? Like the thick plastic stuff? And then you ever heard of saran wrap? Saran wrap and PVC piping differ by a single chlorine atom, I believe it is. Like they're actually chemically almost identical, except one of them has a hydrogen and the other one has a chlorine. And that's the only difference. Now think about those two compounds. They're both kind of plasticky. Saran wrap, super flexible, right? Very, very thin. PVC piping, very rigid. It actually can break quite easily. It can be kind of brittle, so you might need to like seal over like anything that kind of gets cracked, because otherwise the water will seep through it. They differ by one molecule different. So the slightest little tweak in the molecule completely changes its properties. This molecule right here might be aspirin and gets rid of headaches. This compound right here might be cyanide and kills you. You know? And like all that matters is one little difference. So this slide right here basically talks about structural isomers. If you have two compounds that are arranged differently but have the same stuff on them, they're called isomers. I'm sure I've got more pictures up ahead here. Yeah, here's one. This is a butane. So hopefully you're getting better at naming this. Why is it a butane? But is the prefix for 4 in a row. And it's an ANE because there's only a single bond so far. This guy right here is called a methylpropane because there's 1, 2, 3 in a row with a methyl group. These two chemicals are both C4H10, but they're very different. They'll have different melting points, different boiling points. They might even be different colors. Does that make sense? So they have different uses. I think this slide is kind of important here. Butane always has C4H10, but C4H10 is not always butane. Let me say that one more time so that makes sense to you. Butane is always going to be a C4H10. But if I just tell you that it's C4H10 though, it might not necessarily be a butane. It might be a Decepticon in disguise where it peeled off one of these end pieces right here and kind of like dropped it down to the bottom instead and rearranged itself. So you have to be really careful in this unit here that you don't just see C4H10 and say, it's got to be butane because there's 4. Because we don't actually know how they're arranged. The more carbons you have, the more isomers that are possible. C30H62, I found this number a while ago, has 4 billion isomers. Because think of all the different ways that you could arrange 30 carbons and 62 hydrogens. You could put them all in a row, 30 of them in a row. You could put 29 of them in a row and have a branch of 1. You could put 28 of them in a row and have a branch of 2. You could put 28 of them in a row and have 2 branches of 1. This sounds like a really good probability question. Okay, we'll take a 5-minute break because I still got way more to do. Let's pause here. Okay, so here's a slide that just kind of recaps what I've just been showing you here. Here's 3 molecules of the C5H12. Okay. These are all C5H12. So I cannot guarantee for you that C5H12 is pentane. Pentane is C5H12, but there are 2 other C5H12s. Each of these molecules is unique. It has a different chemical property. It has the same chemical structure in that they have 5 carbons, 12 hydrogens. But one of these things right here could cure cancer. The other one could be fatal. Okay, that's a little extreme, obviously. But in this unit here, I said this a few minutes ago, you're really only limited by your imagination. So we're going to start off basic with just hydrogens and carbons, but then we'll throw on some double bonds. Then we'll make things go around in a circle. Then we'll throw in some nitrogens and some oxygens. And I mean, eventually, someone managed to figure out how to make trinitotoluene. Well, where there's a molecule here, once you guys learn about benzene rings here, this right here is a methyl group. This right here is a nitro group. Now, you're really only limited by, let's just try putting new stuff here, basically. So, okay, let's keep going. I think I got some slides where you guys get to do some examples coming up. So here's some notes basically walking you through all the steps about how to name things. But truthfully, I think I've kind of already done that in a way. So why don't we just hop to the examples. Let's name this thing. Okay, so here's the compound. This apparently is a component of gasoline. So it might involve an oct of some kind. How many carbons can you find in a row? I think it's actually labeled on there for you, right? So there's 6 in a row. So call it a hexane. So far, so good? Okay, for the next part, we got to figure out what sort of branches does this hexane have coming off of it? Well, there's a 1 in a row, which is a methyl, and there's a 2 in a row, which is an ethyl. So we need to have a methyl and an ethyl. So which one goes first? The answer is alphabetically. Okay. So since ethyl is an E and methyl is an M, we're going to call it an ethyl methyl hexane. So if you have 2 things and you don't know which one goes first, go alphabetically. Okay, there's actually one more thing I haven't covered though. You see how this methyl group is right here? What if the methyl group, I picked it up and I put it over here instead? Would that change the compound? Yes, it's a different compound. What if I picked it up and I put it over here instead? It is still technically different. That slight tweak could be the difference between saran wrap and PVC piping. Just the littlest difference. Or maybe a different example. I know this isn't organic, but this is H2O, water. Perfectly safe. Drink it. It's good for you. H2O2. No, don't drink that. That's bad for you. That's peroxide. Right? Like, the littlest difference completely changes the compound. So if we just change the order in which this little methyl group is in, it actually changes the compound too. So we actually have to number where these groups happen to be. So the actual correct name for this would be the methyl is actually on the 1, 2. It's on the 2nd carbon. So we're going to put a 2 in front of the methyl, letting you know where its location is. And we're going to put a little 3 in front of the ethyl, letting you know the ethyl group is hanging off of the number 3 instead. If I just tell you have an ethyl and a methyl, it actually doesn't tell you where those groups could be. And the location makes a difference. Does that make sense? Okay, let's try more examples. Let's try to name these ones. So for this one right here, how many carbons can you find in a row? I feel like I can find 5 in a row. Does that make sense? So we're going to call it a pentane. But there's a branch hanging off of it. Right here. The location of that branch makes a big difference. Because, for example, let's say that I put this branch right here. We wouldn't actually call it pentane anymore. Because now there'd be 1, 2, 3, 4, 5, 6 in a row. That make sense? But fortunately, that's not where it is, so that isn't the way it works. But let's say that branch wasn't right here. Let's say it was right here. That would actually change the compound. Because rather than it being on the second one over, it's actually in the middle, and that makes a difference. However, let's say that I put it over here. That's actually the same as the very first one. If you could just imagine in your head that you flipped it around, like literally took the thing and flipped it backwards, it would actually be the same compound if it was over here as if it was over here. So the naming rule says that you need to find the lowest number possible. So let me show you the two ways you could try to name this guy. You could start counting this way. 1, 2, 3, 4, 5. And you could say that on the number 4 branch, there is a methyl. That's one way you could try to name it. But that's actually not correct. Because if you start numbering the carbons from the other side, it's a 2. 1, 2, 3, 4, 5. The 2 is the lower number. So if you have more than one option, we always go with the lowest number in the system. Because if it's on the 2 branch or if it's on the 4 branch, it's actually the same compound, just like rotated. That's all. Okay, let's try the next one. How many carbons can you find in a row? You can find 6, yeah. Some people at first they think there's only 4 in a row, 1, 2, 3, 4. But this isn't an ethyl branch. It's just been written kind of bending around the corner a little bit. So it looks like I've actually got 6 in a row. So I have to call that a hexane. Well, what sort of branches do we have? And where are they? Well, we have 2 different little methyl groups here. So we have to call it a methyl hexane. But because there's 2 of them, we call it a dimethylhexane.
How do we show where they would be?
Okay, good question. So then the last step is we need to tell you where the locations are. Because they could be on, like for this one here, if I start numbering, the lowest numbering system possible would be on the 2 and the 3 branch. So you can go 2, 3 dash is how you'd write it. You'd say there's 1 on the 2 and there's 1 on the 3. Because there were 2 of them, I have to call it a dimethylhexane. The compound I just drew below it has the same basic stuff. It has the same number of carbons and should have the same number of hydrogens. How would you name the one I just drew below here? It would be, you'd actually write it as 2, 2 dimethylhexane. The reason why is you still have 1, 2, 3, 4, 5, 6 in a row. You still have 2 methyl groups, but rather than having 1 on a 2 and 1 on a 3, they're both hanging off of the 2. So you'd have to say 2 and 2 is where their location happens to be, because they're both hanging off the 2 branch. These 2 compounds that I've got on top of each other here, they're isomers of each other. They're similar, and yet they're different. They have different properties. So can you kind of see how this branch of chemistry dwarfs all other chemistry, actually? Right? Because you're really just limited by your imagination. If you wanted to have 62 carbons in a row, sure, go for it. You want to put 50 carbons in a row with a couple of branches of 1 and a couple of branches of 2, and you want to split where they are. Like, there's so many ways you can do this. It's actually, I think it's really cool. I lost track of where my little thing was there. Okay, what am I going for on this slide here? Oh, sometimes to shorten things up, because you can imagine that if you're making more complicated molecules, it's going to be a lot to write out. Sometimes we shorten things. Here's a compound where there's 1, 2, 3, 4, 5, 6 in a row. What would we name this guy right here? Can you guys kind of picture that in your head, what's happening? You've got a CH3 to cap the thing, then a CH2, then a CH2, then a CH2, then a CH2, and then another CH3 to cap the thing. What do we call that guy? How many in a row are there? Any branches? Any double bonds? Hexane. This is another way of writing hexane, but maybe this one's a little bit faster. CH3, because it has to have like an extra hydrogen to cap it. 4 CH2s, like 1, 2, 3, 4 CH2s kind of sitting in the middle there, and then one more CH3 to cap it on the other end. You might get shown chemicals in this sort of format just to kind of save space. Because otherwise it's very tedious, you can imagine, to be drawing these molecules as they get larger. Okay. Okay. Just skip ahead here. Do you guys think you could try to draw me 3-ethyl, 2,4-dimethylpentane? So rather than me give you the drawing and you name it, do you think you could take a stab at drawing this? Give it a try. I mean, whatever. If you totally tank it, who cares? I'll do it in a second. So, see whether you can draw this thing. If you're really stuck, the advice I'd give you is start at the end of the word. Sorry. It's a pentane. So start by drawing 5 things in a row if you're really stuck. Right? 1, 2, 3, 4, 5. Then on the 3 branch, put an ethyl. Okay, so how many is in an ethyl? Okay, 2. So it actually doesn't matter, by the way, whether you draw it going up or down, because it's in 3 dimensions anyways. So I'm going to draw off the middle one, 2 more carbons going up. But if you drew them going down, that's fine, by the way. It's not a big deal. And then on the 2, now I don't actually really care which one's the 2, because like if this one's the 2, then it makes that one the 4. Or vice versa, either way. So this is what 3-ethyl 2,4-dimethylpentane looks like. If you wanted to, you could draw hydrogens everywhere that they'd be required. These are all considered saturated. So I'll use that word more later when I can show you some non-saturated compounds. But the concept basically would be anywhere that there's an open spot, then there should be a hydrogen. But just in the interest of time saving, I never draw them because that's tedious, isn't it?
Can you, with the ethyl, no, the dimethyl one, can you put it up top as well?
Sure, yeah. So it would be just as valid to write 5 in a row. You could put this one on top. You could put those ones on top. Normally, in the interest of like making it look kind of nice, you usually kind of stagger them and make one go up, one go down. But keep in mind, in actual real life, these things are 3-dimensional anyways. So, do you guys remember using a software called JMOL, where you had to like type in a chemical name and it would show you what it looked like in 3D? Yeah, like it doesn't look anything like this, by the way, right? This is just a 2-dimensional rendering. Okay, let's keep going here. Now that we've got the hang of just basic molecules, like I said, you're only limited by your imagination. So someone thought, hey, why don't we try to make these things go in a circle? Right? Like, for example, let me draw you one here. Here's a carbon going to a carbon, going to a carbon, going to a carbon, going to a carbon. I'll just loop it back to itself. Right? Rather than just having a chain that never goes ending, like loop it back around like when my daughter makes like a macaroni necklace, right? You put a whole bunch of little beads on a piece of string and then tie the ends of the string together. This seems logical, doesn't it? Let's talk about the hydrogens, though. It's still saturated, so every carbon needs to be filled up with as many hydrogens so that you have 4 bonds. 4 bonds meaning 8 electrons, right? So this carbon is going to need 2 hydrogens. This carbon is going to need 2 hydrogens. By the way, it doesn't really matter where you draw them, just somewhere. This carbon is going to need 2 hydrogens. This carbon is going to need 2 hydrogens. And that one's going to need 2. How many carbons do I have? 5. How many hydrogens do I have? Only 10. Where'd those extra +2 go? Because it used to be double +2. Yeah, think of it this way. You've got your Kinsey-Adams macaroni chain here, right? You got to rip the 2 hydrogens off the end so that you can then loop them back around the other side. Does that make sense? So anything that goes in a circle has this sort of pattern to it. Cn, H2n. And the way we name these is we call these cyclos. These are fun to say. So if it ever goes in a circle, call it a cyclo something. So let's do some examples. This guy right here is cyclopropane. 3 carbons going in a circle. Now, I haven't talked about this yet. Now's maybe a good time to bring it in. Sometimes, to save time, we just draw purely lines. A triangle is actually a symbol for cyclopropane. What it implies is that every corner is a carbon. That makes sense? Yeah, really it is a time saver. Because like I said, you can imagine, as this gets more complicated, like we're just at level 1 here, right? Like, yeah, it goes forever. Every corner, like every vertice of like your shape is meant to be like a carbon. And then it's implied that you need to have enough hydrogens to saturate these molecules, fill them all the way up. So this one right here is 4 carbons. So that's a cyclobutane. So could you draw me cyclohexane? Well, one way of drawing it would be the structural way of drawing it. It would look something like that. It wasn't my greatest drawing in the world, but there's 6 carbons going in a circle. If this was truly a structural formula, I would take the time and I'd draw in all the hydrogens. Like if you actually had to draw it properly, this is what you'd have to do. Every one needs to have 4 bonds. So hydrogen the guy up. That being said, it's a little tedious, isn't it? So another way of doing it would be to say CH2 bonds to a CH2, bonds to a CH2, bonds to a CH2, bonds to a CH2, and I'm tired of saying that over. That might be slightly faster. I mean, it's the same thing, right? You still have six carbons all going in a circle. But chances are you guys are going to like this after a while. You're just going to start using lines everywhere. That's the fastest way of doing it.
That's what I do.
Yeah. So, by the way, when we're doing our examples, I have no problem with you drawing it like this. On the diploma exam, they cannot ask you to draw something because we don't do written response anymore. What they often do, though, is they're going to give you a compound, and they're going to ask you how many carbons would there be, how many hydrogens would there be, how many oxygens would there be, how many nitrogens would there be, perhaps. Because we'll eventually do some of the other compounds too, right? In this example here, your answer would be there are 6 carbons and 12 hydrogens. So maybe you can envision how they make this a numeric response question. They can't test your ability to draw something, but they'll get you to draw it, so you have to count out all the hydrogens and oxygens and nitrogens and stuff. Still good? Okay, this is the same compound. All 3 of these, by the way, is the same compound. Here's the compound drawn out with hydrogens everywhere. And as you look at it, hopefully you can kind of see, here is kind of your pentagon in the middle. What would you name that then? Cyclopentane. Because it goes in a circle, we have to call it a cyclopentane. But what we have is a cyclo with branches. So like if you can dream it, it's possible. You can have double bonds and a cyclo and branches and carbons and a benzene ring and oxygens. Like you can start like extrapolating and putting all these things together. So, okay, so how did we do branches last time? We've got a methyl and a methyl. So I'm going to say that we have a dimethyl. However, I have to number them. Well, the rule is go with the lowest numbering system possible. Well, okay, so like, let's say I made this the 1, the 2, the 3, the 4, the 5. It would be a 3, 4. But I think I can go lower than 3 and 4. Yeah, 1 and 2 is probably the easiest way, right? Just pick any carbon you want. I'll make this one the number 1, and that one's the number 2. So it's a 1,2 dimethyl cyclopentane is its name. And both of these molecules over here are the exact same molecule, only rotated. Here's 5 in a row. Here's the first one. Here's the second one. They each have a methyl group. Or here's 5 in a row. Now, I don't care which one I started drawing, but here could be the first one. Here could be the second one. It doesn't really matter whether you go clockwise or counterclockwise. They're all the same molecule. All you gotta do is just rotate it. Does that make sense? Okay. Okay, I'm running vastly out of time here. Let me see whether I can give you the Cliff Notes version of how to do double and triple bonds. And then we'll have to pick this up again tomorrow, though. So once you get the hang of the next twist, then we just add a new one. So now the twist is, well, what happens if there's a double bond? What if there's a triple bond? Okay. Maybe I'll come back to the whole unsaturated concept later, because these guys are actually considered unsaturated. And the reasoning is that they actually don't have the most hydrogen possible. But why don't we go to naming them here? Okay, you guys need to skip ahead here. Can you guys find this slide here? I'll just go to this one. We'll do the rest tomorrow. I'll come back to the stuff we skipped. Okay, so hopefully what you'll see in this example, in all of these examples here, is now we've thrown in some double bonds. Okay. The first thing you need to know about naming double bonds is that you change your suffix. Rather than calling them anes, call them enes. Okay. But there's one more twist. Because there are double bonds, we have to note their location as well. So just like with branches, we're going to have to put a number in there to tell you where the double bond is. So let me show you some examples. How many carbons do you have in a row here? Cool. And maybe those are the 4 you have in a row. Okay. Well, to end it, though, I have to end with an ene, because I can visually see that I have a double bond there. Does that make sense? The double bond is your priority number 1. Okay. Now, the further you get into chemistry, there's actually a ranking system of like who gets priority in terms of numbering system. But the double bond takes priority, so we have to give this double bond the lowest number possible. So if I started numbering right here, 1, 2, 3, 4, the way we number a double bond is which number does the bond come after? So if this is the 1, this is the 2, I would say the double bond comes after the 3. But that's not the smallest number I could use. So we'd actually number it the other way. Uh-oh. Apparently I'm saving this thing. The better numbering system here would be to go 1, 2, 3, 4 this way. Because that means the double bond is directly after the first carbon. And this seems kind of dumb, but you put the number 1 directly next to it. So this is going to end with a 1 ene, letting you know that the double bond is on the first carbon. How many in a row did we have? So that's a bute. It really is a bute. So this is a bute 1 ene. Bute 1 ene. 4 in a row. The first bond location is where you will find a double bond. But we're not done though. There's also a branch. What kind of branch is this guy? Methyl. One in a row is methyl. Since there's only one of them, we don't need like a di or a tri. But we do need to note its location. It's on the 3. And it has to be on the 3 because I gave priority to the double bond being on the 1. Does that make sense? That's essentially how you name double and triple bonds. They get priority. You have to throw a number directly in front of it. And then if it's a double bond, put ene, ene. If it's a triple bond, put yne, ine. So why don't we try the next one together? Is there a double bond? Okay, so name it with ene at the end. And then we're going to have to give it its location. I think there's 6 in a row, right? 1, 2, 3, 4, 5, 6. And I think what I've numbered here is the smallest numbering for the double bond. The double bond is currently after the second carbon, so this will be a 2 ene. I guess I should put hex here because that lets me know that there were 6 in a row. And then lastly, we have to tell you where the other group is located. Any ideas? 5-methyl. 5-methyl hex 2E. That's how we name this. Yeah, these things, they have some pretty crazy names. A lot of times, then we start giving them formal names instead. Like aspirin, for example. Rather than naming it its crazy official name, we just give it a generic name instead. Okay, let's do one more, then we'll call it a day. Why don't we try C, I guess. We'll stop there. How many in a row can you find? Okay, so that makes it a pent. But it's an ein this time. Why any? Because it's a triple bond, right? The question is, what number do we put on it?
3.
Not 3, 2. Because in terms of numbering here, if this is 1, 2, 3, if it's between the second and the third, we number it based on like the one it starts with. So since the double bond is starting on the second carbon to the third one, it's a pent 2 ein. And then there's a methyl hanging off of number 4. 4-methyl, pent 2 ein.
That makes sense.
Okay, so here's your challenge then. I did ABC. Why don't you guys try D, and see if you can name these ones here as well. And why don't we start with that tomorrow? And we'll pick up with this tomorrow, and we'll just keep going from there.
Aren't those ones the same?
Actually, they are, aren't they? You're right, they are. Okay, so try naming D, and how about do E, F, G on the next page then? See if you can take a stab at those. Look at F. F's got 3 double bonds in it. See if you can figure out how you'd have to name the 3 different double bonds. Oh, this is so much fun. You guys will actually like this, I think. It's kind of a cool challenge.
It seems a lot easier than the last.
I should point this one thing out. There is no math. There is no molar masses required. There is no, like this unit is very different. It's almost all naming. So it's very different. You don't even need a calculator, by the way. Like we're not doing any sort of calculations in this unit.